To finish off our series on integration, we're going to finally look at differential equations, or DEs for short. Now you may be thinking, we're talking about integration. Why have I mentioned the word differential, which is to do with derivatives? Well, a differential equation contains a derivative. So for example, this is a differential equation because it's got a derivative and it's an equation, it's got an equals. We could put whatever we like on the other side. The differential part of the differential equation means it's got a derivative in, but the process to find the answer, the process to solve, is to integrate. Let's start with example 1. In example 1, we are trying to solve the differential equation dy dx is equal to x squared over y. And what that means is we are looking for a function y such that when we differentiate it, it's the same as x squared divided by that y, divided by that function. And the way we're going to do it is something called separation of variables. And what that means is there are two variables here, x and y, and we're going to separate them. We're going to move them onto two different sides of the equal sign. The y, I'm going to leave where it is. The dx, I'm going to times by that on both sides and move it to the right hand side of the equation. The x squared, I'm going to leave that where it is. But the y, I'm going to times that on both sides and move it to the left hand side of the equation. So what I've done is I've times by the denominators and I've now got something with no fractions in whatsoever. So it looks a bit neater. And what you might notice is, in which case do we have a dx at the end? It's an integral. In which cases might we have a dy at the end? It's another integral. We've not seen many integrals that have a different letter at the end, but if it's y dy, then all that means is you are integrating the letter inside with respect to y in this case. On the right hand side it's dx, it's just like normal. The answer is going to be what we normally do. So we add these big squiggly lines, we get an integral. Let's integrate it then, see what we get. Add 1 to the power, divide by the power, this should be very familiar by now, and then I'm going to add on the constant c. On the left, how do we integrate y with respect to y? We follow the same process, add 1 to the power, divide by the new power, just keeping the letter y rather than x. This time, I'm not going to add on a plus c. We've got two options. You can either add 1 to the left or add 1 to the right. Technically, you could add 1 to both sides, but it would have to be a different constant, so let's not bother with doing that. I usually add it to the right, but I'm not you. Now, this question could have specific instructions saying find y equals, but in this case, this could be an appropriate solution. Maybe you'd want to times by 2 on both sides. Does that make it look a tiny bit nicer? Maybe. Read the question, see what the question says. One last thing about this example, the c is a constant which we don't know, and without any more information in the question, we will never know that c. Any constant, once you differentiate this y, you will get the right derivative. It will work in the original equation, whether c is 1, 2, half, pi, minus 3 million and 10, doesn't matter. Only when you are given more information can you find that c. Only when you are given more information can you find what we call the particular solution. As it is, this is called a general solution. When we know what the c is, when we know what the constant is, it's called a particular solution. On to example 2. In example 2, we need to solve this differential equation. It's an equation and it's got a derivative in. We are going to follow the same method. It's all about separating the variables. Get all the x's on one side, get all the y's on the other. In this case, I have given what is called a boundary condition. So I've told you when x is 1, y is equal to 1. Once we get down to it, we'll be able to find the constant, the c, at the end of the integration, and we're going to get a particular solution this time. Let's find out how we're going to do that. Currently, all the x's are not on the same side, so let's remedy that. What I'm going to do is I'm going to times the right-hand side by dx, like this, And I'm also going to divide the right-hand side by x like this. So divide by x on both sides times by dx. Now all the x's are on this hand side. There are no x's over here. There is still a y over here though. So what are we going to do? We can divide by y on both sides. Once we've done this, we can add the squiggle of integration. The reason that we can do that is because all the y's are dy, all the x's are dx. So we've got an integral with y with respect to y and an integral with x with respect to x. If you had an amalgamation of x's and y's, it just wouldn't work itself out. That's why you've got to make sure they're all by themselves on their own side of the equation before you add the integral sign. At this stage, it just turns into an integration game. So make sure you've got your integrals down. You recognize the different styles of integration, whether you have to use certain rules, whether you have to use certain tricks, or whether you have to know that the integral of 1 over y is ln y. Make sure you've got that in your head of which integral am I going to be using, because it's going to make differential equations so much easier if you can just pluck it out and know exactly what you're going to do straight away. So on the left, ln y. On the right hand side, bit trickier, but with a bit of simplification we can sort it out. So this is the same as the integral of x plus 1 over x, which if we integrate that, we're going to get x squared over 2. And then the integral of 1 over x is ln x. And as I said before, my personal preference is to add the plus c on this side, but it's up to you where you add it. It's also up to you at what stage you find your constant of integration. Personally, I'm going to just shove in x and y now and see what happens. So when x is equal to 1, y is equal to 1. So let's sub it in here. 1/2 ln 1 is 0 plus c ln 1 ln y is 0. So in my case, when I work it out, I get c is equal to minus 1/2. If your c is on the other side, you're going to get a different value of c. If you rearrange it at some point and then try and put x equals 1 in and y equals 1 in, you'll get a different value of c. It's okay. They're all equivalent. Just depends on when you put the values in. So in the end, we get ln y is equal to x squared over 2 plus ln x minus 1/2. And that is our particular solution for this case. We could rearrange it, we could get y equals, we could do some finagling and get it something to do with e, but I'm going to leave it like that. That's good enough for me. Over to you then for exercise A. I'd like you to 1. Separate the variables x on one side, y on the other. Integrate both sides, rearrange, and solve this differential equation for me. In this case, I don't mind what form it's in. So as long as it's been solved, I'm happy. Okay, time for something a bit harder then. In this case, there's more algebra, there's more letters there. It is looking a bit more complicated, but trust me, if you can integrate everything, then you can do this. It still follows the same pattern. We still need to separate the variables, so let's do that first. How are we going to get all the y's on one side? We're going to divide by y squared minus 1 up here to get 1 over y squared minus 1. I'm also going to, in the same step, feel free to do it in multiple steps if you need, I'm also going to times by dx. Everything else, the x plus 2 times by x minus 3, I'm going to leave where it is because it's already on the side with the other x's. Now, because all the y's are on one side, and because all the x's on the other side, I can add our integral sign. Now, I'm not going to specifically go through these integrals. I'll briefly talk about how to find them, but this is one of those integrals that you should be able to recognize and be able to answer. There's nothing in this method now that involves something new. It's all back to what we've seen previously. So to briefly discuss it, the first integral there, we are going to be separating y squared minus 1 into partial fractions. And then once it was in partial fractions, we would integrate it using this ln rule that we've talked about before. For the right-hand side, we'd do exactly the same thing. It's more partial fractions, and then once it's written in partial fractions, it's another use of the ln rule. So as I say, I'm not going to go through that full example because we've seen that type of integral before. If you can integrate that, then you can solve the differential equation. And then back to you. Could you solve dy dx is equal to cos squared y divided by 1 minus x squared? Alrighty, so now we know how to solve a differential equation, but we don't yet know how to create a differential equation or form a differential equation. These are the two types of differential equations that you could get. If you know how to solve, you can do most questions, but sometimes you need to know how to form one in order to get started on a question. There's two main things I'd be looking out for in a question where you have to create the differential equation yourself. Those are the rate of change of something and the units given in the question. So it could be centimeters per minute, could be something per hour, any units given in the question. That's something to look out for. When you see rate of change, you need to be thinking it's a derivative first and foremost. It's a rate, so it's a derivative. And we are talking about a rate with respect to time. So d something dt. It might be the volume that's changing over time, the rate of change of volume. So let's put a v there. It could be the rate of change of the length. So we put an L there. It could be the rate of change of the height. If you really want to be confusing, the rate of change of the temperature, dt dt. When you read through the question, that is something that I would be pulling out of the question and turning into maths. As soon as you see rate of change, get down your derivative. As for the units, it's the same sort of idea. If you see centimeters, then you are talking about the change of a length, for example. It could be height, it depends what the question says. And because it's over minutes, that means it's with respect to time, so dt. If it said centimeters cubed per minute instead, that gives you the indication that it's not talking about length anymore, but it's talking about the volume or the capacity instead. So it's just something to keep your eye on. Okay, here's our example. So be prepared for some of these to be very wordy. This isn't that wordy, but it could have 5 times as many words for certain questions. In our case, the rate of change of the volume of a sphere is 10 centimeter cubed per second. This question is definitely going to be easier to answer than it is to say. We see the rate of change, so straight away it's a derivative, and it's a derivative with respect to time because it's the rate of change over time as something is changing over time. What is it the rate of change of? It tells us it's the rate of change of the volume. As long as you define your letter, you could call volume X if you really wanted to. I'm going to call it V for simplicity's sake. What does it tell us the rate of change of the volume of the sphere is? It tells us it's 10. So what am I going to do? I'm going to put the number 10 here. And that's it. That's our differential equation. The letters are different. It's not y anymore, it's v. It's not x anymore, it's t. There's a number, not an x or a y on the other side. That's fine. It's still an equation because it's got an equals, and it's still a differential equation because it's got a derivative. That's it for this question. Okay, example 5. Again, slightly harder. This time, the rate of change of the temperature of an object is inversely proportional to the current temperature. And we're looking, same goal as last time, write down a differential equation relating to the situation. Still says rate of change, so I'm still going to write down a derivative d something dt. What's it the rate of change of? It tells us its temperature. So I'm going to do the confusing one, dt dt, with t temperature being capital and t time being lowercase. You have to think all the way back to GCSE now. What does it mean to be inversely proportional? You must remember that means it's k over something, where that something is going to be a variable. What's it inversely proportional to? It says there the current temperature. And what letter did we decide was temperature? We said capital T. So this time dt dt is equal to k over t. Lots of t's. And now an exercise for you. The rate of change of an area of a shape is proportional to the area squared. And I would like you to write a differential equation that relates to this situation. So for example 6, our last example, we know how to create a differential equation. We know how to solve a differential equation. In this type of question, which is definitely going to be harder, but also you'll be rewarded handsomely with marks. We're going to combine all that we know with the chain rule in differentiation in order to make the questions a bit wordier, but a bit more fun. This question says that the rate of change of the area of a circle is proportional to the perimeter. This time we're told that the perimeter is 10 and the rate of change is 4. So only when the perimeter is 10 is the rate of change 4. When the perimeter is bigger, the rate of change might be bigger. When the perimeter is smaller, the rate of change will be smaller. What we're looking for is the rate of change of the perimeter, specifically when the area is pi, i.e. when the radius is 1. So lots of words. How on earth do we crack something like this in the same way as before? Still says rate of change, so I'm going to write down my derivative. What's it the rate of change of? It's the rate of change of the area, so I'm going to put A here. And we're told that that's proportional, so I'm going to pop a K down, proportional to the perimeter, so I'm going to pop a P down. What's more, we're told that when the perimeter is 10, the rate of change of the area is 4. So that's dA dt again is equal to 4 when P is equal to 10. There's not much we can do at the moment because there's A and T and P and K, to be honest. There's lots of letters and not enough equations. So what we are going to need to do is we are going to need to find some relationship between A and P and use some derivatives and the chain rule in order to get many equations, amalgamate them all together into something that we can actually solve. The one piece of the question that we haven't used yet is the fact that the shape is a circle. And we know, or at least you should know, that the area of a circle is pi r squared. So if we differentiate this, we're going to get dA over dr is equal to 2 pi r. But that's equal to the perimeter or circumference of a circle, 2 pi r. Also, if you were to take P as 2 pi r, you could do dP dr, and that will give you the derivative of P with respect to r, which would just be the constant, the number, 2 pi. I know it seems a bit unrelated at the moment, but we have got dA dr and dr dP being connected together, and that will connect us to dA dt once we use the chain rule. The chain rule says that we can add whatever we like as long as we times and divide by it. So in the original dA dt, we don't really want the A because the question is wanting the rate of change of the perimeter. So let's put maybe an R there instead. And that is more helpful because dA dr, that is supposed to be an R, is something that we've got, is P. So this will be equal to Kp, as in the original question. I'm going to take that one step further now. Rather than writing dr dt, I'm going to make use of another chain rule. I'm going to write it as, this time, dr over something times by something over dt. What's the most useful letter in this case? It's going to be P, dP. Sorry about the handwriting, it's going a bit slow at the moment. We're going to add in dP because the rate of change of the perimeter is the thing that we're looking for. So P is definitely the most useful letter here. dA dr, down here, that's P. dr dP, do we have that? Not exactly, but we've got the reciprocal. So that's 1 over 2 pi. dP dt, we don't have that, but that's what we're looking for. So dP dt, I'm going to leave it as it is, like this. So I'll quickly sort that out, make it look a bit nicer, make everything go onto one side, and we'll see what it looks like afterwards. So once we simplify that, we get that dP dt is equal to 2k pi. So what is the rate of change of the perimeter when the area is pi? Well, there's actually no perimeters in this differential equation. So the rate of change of the perimeter is the same whatever the area is. So all we need to do now to finish this off is just actually find k. We don't need to solve the differential equation in this specific case, but in another case, you might have to. Let's see if we can find what k is then. So we know that dA dt is kp, and we also know that dA dt is equal to 4 when p is equal to 10. So what that tells us is that k times by 10 is equal to 4, which means we can work out what k is. K is going to be 2/5. Putting that all together, that tells us that the rate of change of the perimeter, which we know as dp dt, is going to be 2k pi, or 4/5 pi in our case. When I wrote the question, I didn't think about the fact that it wouldn't matter what the area is, the rate of change will always be the same. In another question, you might have to, as I say, solve it. You might have to sub in some values specifically to the derivative. In our case, we get 4/5 pi as the final answer. Last example for you to finish off then, the rate of change of the volume of a spherical balloon is inversely proportional to the radius of the same balloon. I'm also giving you the information that when the radius is 2, the rate of change of the volume is 6 centimeters cubed per hour. My actual question, find the rate of change of the radius when the volume is pi centimeters cubed. And there you have it, that's how to do differential equations, and that's the end of our integration course. Make sure to watch past paper videos and example questions to really make sure you've nailed this topic.